Okay, now let's solve this problem with Ansys. So first of all, we need to create study static structural. And I hope you now understand why we need to do this first, because we need to find or determine the stress stiffness matrix first that would go into the eigenvalue problem next. So we need to run a static analysis in the first step. So the material is structural steel. That is fine. What we need to know for static to understand if this material fails under quasi-static loading is the yield strength under compression, which is 250 megapascals for this material. So in my Excel sheet here, I am also doing the calculations analytically. So I have taken this value here. So this is 250 megapascals. And these are the dimensions that we already know. So this is the external diameter, this is the thickness, this is the length, and this is the Young's modulus. And the other things, the ones shown in red, they are driven from this. So this is the internal radius. This is the second moment of area of the cross section, which is a hollow circle. And this is the cross-sectional area. So second moment of area and cross-sectional area. And next I have used these equations, this one, to determine the critical load or critical buckling load for mode 1. And I have done this for mode 2 as well, which is just this one times 4. So I have analytically solved this problem. This was the buckling analysis, and this is the static analysis, which essentially for static analysis, what I've done is that I have multiplied the cross-sectional area by the yield strength under compression, which gives me the maximum load that we can apply to this rod in compression to cause failure. So this stands for failure analysis under static loading. And this one shows the critical buckling load. Well, these are all analytically done, but I would like to do the buckling analysis now with FEA. So we need to define the geometry first. So I will open the design modeler. Now in design modeler, I choose this plane, and I will turn on the grid like this and use a snap. And here I put the major grid size to 2 meters, which is the length of our beam. This will just help us with creating our sketch. We create a line, goes from 0, 0 to 2, 0, 2 meters. So this is done. Now I will select this sketch, I go to concept and create lines from sketch, and now I just hit generate. It will generate the body for me. Now we need to define the cross section. The cross section is circular tube, and we need to define the internal diameter, internal radius and external radius for this beam. So essentially I need to divide this by 2, and I need to divide this by 2, and I will just insert these values here. So 10.7 and 8.4. Okay, so diameter radius is defined now. And what I need to do now is to assign the cross section to the tube. Okay, so this is done. If you want to view the cross section itself, you can just do that, and you can see now we've got the cross section defined. Okay, we are done. So we can go back here to the workbench and open the model. So essentially it will now load the geometry, load the material properties, and we can continue with setting up our static simulation. Okay, our model now is loaded here. I change the display to front like this. So we can as well show the cross section here. So that is a visualization of our tube. Great, so we've got the geometry, which essentially gives us the cross-sectional area, length, and second moment of area. These are the properties we need, geometrical properties we need to formulate the structure stiffness matrix. We also need material properties in order to do that, which are given here. Cross-section is defined here, so these go all together into a structure stiffness matrix. Now we need to discretize or mesh the structure. So here I just use the default setting in terms of the number of elements across the length, and I mesh this. So you can see now it has used a number of elements to discretize this line. These are beam elements. Now we need to define boundary conditions. So I insert boundary conditions. So one end was simply supported, with essentially it will fix the translations of that end. So I will apply this simply supported condition here. And the other end was roller joint, right? So we don't have a roller joint here, so I need to define what degrees of freedom are fixed and which ones are free. So essentially in X direction we can allow translation, the rollers allow that, but the other two are fixed. And what I do next is applying a force. I apply the force here. The amount of force, this is an arbitrary amount as we discussed before, but I said that good practice is put 1 here, so I need to apply this as well. Okay, so this is the force applied. Well, you may wonder why I'm applying 1 force. So this structure is in equilibrium, so if I apply a force here and this is free to move in X, this is not free to move in X, so essentially this will be subjected to the same amount of force in the opposite direction because of the static equilibrium. So you don't need to apply any other force here. The other thing is that you may wonder why this is not putting the beam in compression. Again, fine, when you do the buckling analysis, the sign will tell you if the load should be positive like this or it should be negative, hence in compression. Okay. If I run this simulation, you will see that it will not succeed. Let's see. So now this is forming all those matrices, the structure stiffness matrix, vector of nodal displacement, vector of nodal forces, and inverting that structure stiffness matrix, but it will run into a problem. You will see in a moment. So this is the error. The error is telling us that there is pivot, and if you look at the reasons for that, so we have, this is what we call the singular stiffness matrix problem, or it's calling it pivot warning or error. You can see one of the reasons is that we have under constrained model. And that is the reason that we've got this error here. So if you remember, I explained that not having adequate support can lead to this problem. So you may wonder what degree of freedom is now open here. So if you remember the beam elements, they could have bending, but they could also have torsion, which means rotation about their own axis. We have not fixed that rotation. So essentially it means that if we set this beam in rotation about its own axis, there is nothing to resist it. Therefore, that degree of freedom is completely free, and that's what leads to the singularity of the stiffness matrix. Hence, I'm going to apply a boundary condition which will fix the rotation about the x-axis. So I choose that point and I fix x. I don't need to fix y. Actually, we shouldn't fix y, and we don't need to fix z. So essentially, if you fix y, then this will not be a pin joint. It will be a fixed boundary condition. Now, if I run this simulation, it should succeed. There we go. So we've got the solution, no problems at all. And if I look at deformation, so I need to evaluate this in the results. And this is the deformation, okay? So the animation would look like this. Yeah, essentially we are stretching this beam. Or if we had a negative force, we would be compressing this beam, but nothing that would look like a buckling mode. So essentially we need to do the eigen value problem solution now. Okay, in order to do that, now by doing this, we have determined the stress stiffness matrix. Now this stress stiffness matrix should be fed into the eigenvalue problem. So here's the eigenvalue buckling. If you just drop it here independently, Workbench will not understand that what is feeding the stress stiffness matrix into the eigenvalue buckling problem, right? So you need to tell Workbench where these results are coming from. That's why you would drop this eigenvalue buckling on solution here so that it can make a link between these two. You see, visually and nicely, Workbench is showing that the solution from this static simulation is feeding into the eigenvalue buckling. Essentially, this is determining the stress stiffness matrix for the eigenvalue problem. Great. So let's go to the setup of the eigenvalue problem. So you see here, this is the pre-stress. Essentially, this is what we call the stress stiffness matrix comes in. You can define in which stage of the static solution this should come from. Sometimes static solutions may have several time steps, so you define one load and increase the load in different ways. But in our simulation, the previous one, we had only one step, which was one step of loading to unit value. Hence, even changing this to time step or load step or time is not going to make any difference. Okay. Next, analysis settings. So you can see here the maximum modes that we tell the software to find is 2. I'm going to change this to 4, so I want to see the first 4 buckling modes in this solution. Now I'm going to solve the eigenvalue problem. So you remember now this is forming the eigenvalue problem and finding the solution that would make the net stiffness 0. Essentially, it will find the critical load and the associated buckling mode shape for that critical load. Okay, this is done now, but we do not see anything because we need now to add some plots like deformation for mode 1. I'm going to add another deformation, and this one I make it mode 2. This one deformation mode 3, and this one deformation mode 4. So sometimes you may run into an error if you start evaluating, if you choose mode 4, but you have not set here in the analysis to calculate 4 modes, then it will tell you that I do not know what is mode 4 because I have not solved it yet. So make sure that you have asked for enough modes. Perfect. So let's look at total deformation in this one. So if you look at this graph, actually, this is interesting. So it seems Ansys is now sorting the modes based on the lowest value. And here's the lowest value is negative 12,000, more or less 12,000 Newton. But you know that buckling would happen under the smallest magnitude of the load. So essentially mode 3 and 4 are happening first, and then mode 1 and 2. This is the consequence of us defining the load in a positive direction in tension. If we would have put it in compression, these values would have been positive, and then mode 1 and 2 would start from 3,142. Okay, let's look at these two. So this does look like what I was showing previously in my slides. So this one, yes, this is mode 1. And I have done the analytical solution. The value that I get from this equation is 3,102, and what Workbench is giving us is 3,142. So there's 40 newtons difference, and this is related to some of the errors that we have when we convert our mathematical model into a finite element model. So now you know that error is related to discretization. So if I increase the number of elements that I'm using here, I can manage and reduce that error. But to be honest, 40 out of 3,100 is really small, so we can accept that difference. Again, this mode shape is very much similar, but it is in a different plane. Now it is in the XZ plane. And similarly, this is now a full sine deformation, very much like this mode shape that we've got there. And the next one should look the same, but in a different plane, right? So this is now in the XZ plane. So essentially mode 1, 2, and 3, 4, they are the same, but mode shape is in a different plane. You can avoid it if you fix rotation about the Z axis, okay? So you make it really like a pin joint at this point where we had the simply supported boundary condition. I hope you have enjoyed this tutorial. Thank you for your attention.